Lesson 69 deals with the first part of integration by parts, and this is going to be a way of substituting for functions that we can't integrate just kind of by guessing or knowing what the integral is. Something like when we have two functions multiplied together and we want to integrate this, and we could try to do a u substitution for for x, but you still have this x out here. So we know if we had like a sine of x squared, then we could use substitution for something like this. But if we just have the sine of x, we don't have any means of integrating this right now. So this, when you come across an integral problem, check to see if we can do substitution or if it fits one of our other things, or if you can even multiply terms together to get something simpler. But if not, it's probably an integration by parts type question. So the first thing we want to do is we want to show what integration by parts is. There's actually a formula for it that we're going to come up with. So let's take a look here. We have, we actually start with a differential. We start with the product rule. We have d of u times v, so you have two different things multiplied, is equal to, using the product rule, the first times the differential of the second, plus the second times the differential of the first. And what we're going to do now is we're going to integrate both sides. We want to integrate that. So on the left, the integral and the differential cancel each other out. And then on the right, we have the integral for that. And what we're going to do is we're going to solve for this term right here. So we're going to subtract. Well, first we're going to write this. We're going to show that the integrals cancel here. We're going to subtract this from both sides, and we end up with the integral of u dv equals uv minus the integral of v du. And what this is going to do is this is going to simplify our integral into just a multiplication problem, and then subtract. Hopefully what we do is we choose our u and v correctly, so this becomes a simpler integration problem. This equation is the basis for integration by parts. Very important to make the right choice for your substitution, or you could actually make it more difficult. So how do we make that choice? Here's kind of a clue or a hint for that. Look at the other side of the equation and assign u so that the derivative of u becomes simpler. So we want to choose u so the derivative becomes simpler, and at the same time, when you take the integral of dv, it doesn't become more complicated. So the integral of dv does not become more complicated. All right, so that's how we want to choose our variables. So you are going to need to know this formula for integration by parts and then be able to use it well. On each of the following slides, I'll have it on there, but you will need to memorize that. So here we go. Here's the first one I actually just mentioned. We have the integral of x times sine of x dx, and already talked about how this wouldn't be able to, we couldn't use our standard means of integrating this. And so we want to write this as u times a differential. So we're going to need, in the differential, we'll put this dx. I usually set up this little box here with 4 compartments, and in the top right, this will be my u, and in the bottom left, sorry, the top left, this will be u, and the bottom right, this will be the dv. And what we'll do is we will integrate to help us find, because we need both u and v, and we need du, we're going to integrate the dv to help us find v, and then we're going to differentiate the u to help us find du. And so we make our 2 choices first, and then we find these other 2 things and we can fill in our formula. So what's a good choice for these? So remember, u, when you differentiate it, shouldn't become, or it should become simpler. So we could differentiate x. We could put x here. Differentiate would just be dx. That becomes simpler. We could put sine x here. If we differentiate sine x, we get cosine x, which isn't more complicated, but it's also not more simple. And so it seems like we want to put an x here. Let's just check that. Let's say we would put sine of x here, because when we want to integrate it to not become more complicated, and when we integrate sine x, we get negative cosine, which isn't any more difficult than sine of x. So that's what we're going to do. So the first thing we do is we fill in here. We're going to let u equal x. Again, we're letting u equal x, because when we differentiate, we have two products here, or two functions here. We have x and we have sine of x. Our choices are to put x here or let u equals x or u equals sine of x, and it seems like letting u equal x is the better one, which means down here for dv, we're going to let dv equal sine of x. And then what we do, we differentiate to find du, and we integrate. So the integral of sine of x is integrate both sides, you get v equals negative cosine x. And now what we're going to do is do some substitution. So here is our rule. We're going to plug in. So we plug in u, which is x. We plug in v, which is negative cosine x, minus the integral of v, negative cosine x, times du, which was dx. So we do all that substitution, and now we just figure out what this is equal to. This is just going to be negative x cosine x, and the integral of negative cosine x is sine x, and we put our plus c. And so there is our answer. Coming to our next one, the integral of natural log of x dx. So we don't have much here. We have a natural log of x and a dx. And so we don't have a lot of choices on what to do here. We could try putting natural log of x dx here, but we're trying to figure out what the integral of that is anyway, so that's not going to work out. So what we're going to do here, which this is an important one because we don't know the integral of natural log of x, so this is good that we're finding this and we can use this integration by parts. So looks like all we can do here is we can put natural log of x in for u. And then, so remember this is our u on the top left, our dv, which just has to be dx, and when we integrate that, it's going to be simpler. It's just going to be x. So we'll differentiate. So we have our u and our dv. Now we need to differentiate to find du. So the differential of natural log of x is 1 over x dx, or just dx over x. And if we integrate here, we just get v is equal to x. And so we want to use integration by parts. So we make in our, here's our formula, uv minus the integral of v du. We'll plug in all of our different values. So u times v, natural log of x times x, minus the integral of v, x dx. Now that we've made the substitution, actually over here on the right, we can cancel this, so we're just doing the integral of dx. So we have x times the natural log of x minus the integral of dx is just x. So, and then plus c, and there we have the integral of natural log of x dx. So this is a good thing to memorize. Natural log is an important function, so make sure you know the integral of natural log. And coming to our last one here, we have the integral of x times e to the 2x dx. And we might think, oh, maybe we can do this just our regular way, not using new substitution or not using integration by parts, but we won't be able to get this x here. So let's make our choices here. We have two functions that we can work with. We have the x and then the e to the 2x. So we have 1 and then 2. So our options are we could let u equal x and dv equal e to the 2x dx. Or our other option would be to let u equal e to the 2x and dv to equal x dx. If we put x in here, this does become simpler. It would just be du equals dx, and this one, if we integrate, it doesn't become more complicated. It would just be like something to the 2x. So that seems like a good choice. We could look at this one. The differential of e to the 2x does not become simpler because it's just 2 times e to the 2x. So it looks like the blue one is going to be the choice we want to make. Again, sometimes what you do is you make the wrong choice, you go through and you figure out, oh, that's more complicated, so you might have to scratch that, go back and make a different choice. So we're going to let u equal x. We're going to let dv equal e to the 2x dx. We want to differentiate to help us find du, which is dx, and then we want to integrate. You can think through that integration. It's going to be 1/2 e to the 2x. We need the 1/2 there to cancel with the 2. So coming over here, we know our formula for integration by parts is right here, uv minus the integral of v du. We can now go ahead and make our substitutions. Plug in u, which is x, plug in v, which is 1/2 e to the 2x, minus the integral of v. V is just 1/2 e to the 2x times du. Substituting there, you just put in dx. So there's what we have. Our product on the left there, we can just do 1/2 x e to the 2x. We can integrate 1/2 e to the 2x, and we're going to get 1/4 e to the 2x, and we should put plus c. And those are some examples of using integration by parts. Integration by parts is when you have a product of 2 functions, and you can split it into 2 parts, one being u, the other one being dv.